Looks like you made an algebra mistake there. But something that would have been better is, the way to avoid those algebra mistakes is, why don't we just do the calculation up here? If we just do the calculation up here, then we don't have to carry the 1 divided by 0.3 around.
It's 3.3, right?
Oh, calculator? Where's my calculator? How did you know? Okay. What are the units on that?
Wavelength is meter. No, it's meters. Yeah.
Yeah, it's a length, so it's meters. Sometimes you could call it meters per cycle, but actually it's more common just to call it meters. It's just the length of the wavelength, so that's meters, 100 meters. Okay, this is a generally an important point for problem solving. If you're worried about making math mistakes, it's better to do the calculations up front. Rather than carrying around this 1 divided by 0.3 over here, why don't we just do the calculation, and then we don't have to. So remember that anytime you have a fraction, that's really a division. A fraction is really a division. This just means 1 divided by 0.3. All right, and then we would plug that number into here, and then we don't have to do as complicated algebra to work through the equation. Okay, all right, so again, the point of the flowchart here is on the test, you wouldn't just go from here to here, you have to go 2 or 3 steps. So you have to ask, where am I starting? Well, I'm starting here with the period. And where's my destination? Well, my destination's here with lambda. And then you say, oh, here's the path. This is the formula that takes me to the frequency, and then this is the formula that takes me to the wavelength. Okay. So the hard part is not that knowing the formulas, but the point is people have so many formulas in their cheat sheet, they don't know what order to use them in. So it helps to have them kind of organized like this. Okay. Well. Now remember that most of the stuff that we've been talking about works for either waves or just any old oscillation, right? So you could talk about, say, now this is only for waves, I guess. Only waves have a wavelength. But any old oscillation would have a frequency or an angular frequency. For example, you could talk about, say, that spring that was oscillating at 8 cycles per second. You couldn't talk about the wavelength of a spring. It doesn't have a wavelength, but it has a frequency, so it has an angular frequency. So let's go back and talk about these oscillations again here for a second. Now, usually when we're talking about these oscillations, we're talking about oscillations that are generated by simple harmonic motion. That's probably a term that you heard in class. Simple harmonic motion is the type of oscillation that you can be focusing on in class over here. Let's see, is that the best thing to work on now? Yeah, let's do that. So let's say we have, say, a spring. Let's say this is the natural length of the spring. And let's say we pull it out to here. So here's a mass M that's attached to it. So we've pulled the spring out to here. What's going to happen to the spring when we let go of it?
It's going to oscillate back and forth.
Yeah, the spring is going to go into here. It's going to go past the natural length. Its inertia will take it past the natural length. So it'll go from expansion to maximum compression, and then back to expansion, and then back to compression. And if there was no friction, which is what we assume in this class, we assume no friction, it would keep expanding and contracting around the natural length forever. So if you pull the spring away from the natural length and then let go of it, if you imagine there's no friction like we do in this course, then it would just keep oscillating forever. And you could ask, what's the period of that oscillation? That is, how many seconds does it take to go through a cycle of oscillation? Or you could ask, how many cycles of oscillation does it go through in 1 second? That's the frequency. And you can put that into an angular frequency too. The wavelength doesn't apply here because this isn't a wave. But these other 3 concepts here would apply. Okay, So let's see if we can figure out how to figure this out. Well, there's a key formula for this. That's based on K. Have you seen the K for a spring? I don't even remember. We've talked about that together.
Constant?
Yeah, we talked about springs together? I don't even remember. Okay. Have we? Yeah.
Yes.
Okay, yeah, this is our spring constant. Or in general, this doesn't have to be a spring, but anything that oscillates with simple harmonic motion, this would be the constant of that oscillation over there. But we can think of this as a spring constant, okay? So this is our spring constant, say. Do you remember, did we say that K measures the stiffness or the looseness of the spring? We talked about that?
No.
Okay, so K is how stiff the spring is, or tight. K is how tight the spring is. Okay. So what we'd like a formula that would allow us to figure out omega if we know K. Well, let's say K is big. Does that mean the spring is loose or tight?
It's tight.
Because this is the stiffness of the spring. So it's a tight, stiff spring. Do you think that that means it's going to oscillate quickly or slowly?
Slowly.
Maybe that's a little hard. So let's see. Why is this oscillating? Well, when you let go of it, what happens is that the spring force pulls you back.
Oh, okay.
Right?
So then I see.
Yeah, and because
if
this.
if the K is big and the spring is stiff, that means that it's going to take more energy for it to pull apart. So that means that it's going to flow back.
That's not what I was going for, but that's a good explanation. Yeah, that's a good explanation. So that's another way of putting it. Yeah, since it's a very tight spring, we had to put a lot of energy into it to pull it out. That's actually better than the way I was thinking of. So we had to put a lot of energy in to pull it out. All right, and then we're going to get a lot of energy back when it starts coming back in. Maybe stiffness isn't the best word then, because it sounds like an old stiff person that's hard. It's hard for them to move.
Yeah.
But somehow the point here is that the spring really wants to get back to the natural length. A stiff spring is really unhappy to be out here, and it's really anxious to get back to the natural length. So it yanks the mass back really fast. But then when it gets to the natural length, it shoots straight past it because of its inertia. But then it goes back really quickly to the natural length again. So anyway, a stiff or a tight spring. But what did we decide? Is it moving fast or slow?
Fast.
Yeah, it's oscillating fast. So should omega be big or small?
Large.
Because that's a measure of fastness. So we just decided that there should be a direct relationship between K and omega. The bigger K is, the bigger omega should be. Okay. And how about the mass? If the mass is big, do you think the spring is going to move fast or slow? Because it's hard to move massive things. Yeah, it's hard to move massive things. If there's a great big block attached to the mass, it's going to be tough for it to move. So which of these would be a better formula for omega?
The second one?
Because there's an inverse relationship between m and omega, because m is omega is a measure of fastness. When the mass is big, we want that in the denominator to slow the frequency down. Okay, so this should just be kind of common sense that a tight spring is going to have a big omega, and a great big mass is going to lower the frequency. It's not common sense, but it's true that you have to take the square root. So we just memorize that we have to take the square root. But a lot of times people forget who goes on top and who goes on the bottom. Well, I guess you'll have it in your cheat sheet. But even if you lost your cheat sheet, it should be clear who goes on the top and who goes on the bottom of this fraction. Because this has a direct positive relationship on the fastness, and this has an inverse relationship on the fastness. And we have to memorize and take the square root. All right, so now we have another element in our flowchart. If you know K, you can figure out omega using this formula. So here's a problem. If K is 8 newtons per meter and the mass is 3 kilograms, what's the period? If you want, you can calculate the answer. If you want, you can just tell me how you would do it.
When am I calculating the period?
Right.
So, I have mass, so by using this, I can calculate omega.
Yeah, what formula would you use for that? Good, that's right.
And then I can use omega to calculate the frequency.
Using which formula?
Omega equals 2 pi times the frequency.
So you'd have to do a little bit of algebra on that to find the frequency. That's good, that would tell you the frequency.
So omega over 2 pi.
Would tell you the frequency, good.
Tell me the frequency, and then to find the period, I would take the inverse of the frequency.
Take the reciprocal. On your calculator, you can just do 1 divided by that.